To do the preprocessing, we will first load database, then we will filter by columns, after by features, and finally we will delete and replace missing values. First, we convert the time column to date time and extract the minute value from it. Then we only take the rows whose minute is even. This is, we eliminate the rows with even minute and show again the dimensions of the database. In this section, we delete columns other than time stem, accelerometer start, and gyroscope stand min, and if t sensor features. Thus eliminate most of columns and leaving only the most representative to problem solution. First, we go through the new reduced base in search of null values. In case you find null values, they will be replaced by the mean values, since it is better work with the mean of the values than with null values. After that, we store the result in a new database, making it simpler to work in the principal component of the analysis.
Hi, I am Iván and I will talk about principal component analysis. This consists of seeing how related our data is. We will talk about normalization of the data, covariance, and Pearson. To normalize the data, we will use the standard scalar, and we are going to use two components and exclude time stamp. The two components we are going to call PCA1 and PCA2. After this, I will enter the data in a data frame that I have created and make a graphic representation to interpret it. As we can see, the data are arranged on the ascending diagonal axis. It only takes that direction, which means that is the one that maximizes the variance. Then we can say that our data are related. Anyways, we have carried out a study by pairs of variables calculating their covariance, like we can see, and the correlation coefficient of Pearson that we will see. And it has turned out that there are variables that are very related to others variables and others that are not so much. For example, some very strong relationships are the covariance of accelerometer stat J median FFT and gyroscope stat J median FFT. The covariance of accelerometer stat X median FFT and the gyroscope stat X median FFT. For example, for Pearson, some very strong relationship are accelerometer stat J median FFT and gyroscope stat J median FFT. Like we can see, covariance and Pearson are like the same, and we can see that the same variables are related. So this is all for the principal component analysis, and now we will study the clustering.
Hi, I'm Pablo Palomino and I'm going to explain you the clustering process. In that, we run the hierarchical clustering algorithm to see how the data is distributed, and then we run the Cummings clustering to see the groups of our data. Hierarchical clustering. How the data is distributed? We don't need the number of clusters before, but we need to determine the metric, the distance between clusters, and the cut. These algorithms work like as cluster as elements and the pair of clusters close to each other joining one and repeat. As the hierarchical clustering is very complex, we decided to reduce our data because we have 39,000 rows and our memories collapse. In order not to lose information, we group the rows by hours with the mean value. This allows us to run the hierarchical clustering without problem. We normalize our data using mean mass scalar, compute the similarity matrix using Euclidean metric because we have numeric values, and we use complete distance between clusters. Applying the cut about 15, we obtain this dendrogram. As we can see, we have 4 clusters of elements by cutting at 15. To see the numbers of elements in each cluster, we add a column groups to the data frame with labels. We group by, and we can see the size of each group. As we can see, in the third cluster, we have 3 elements, so it is a cluster of outliers. And in the first cluster, there are more data and is the more density cluster. Okay, let's apply Cummings algorithm to our normalized data. In Cummings, the number of clusterings is predefined. This algorithm is based on minimization of internal distance. We use a K value of 3. We use the random init method. We try to use Cummings++, but we obtain the same result. And we obtain the next 3 clusters. We detect that green cluster has some outliers, and in the purple cluster the data is denser than in the other clusters. That's it, the data is more concentrated. We group our data per hours, so the result of TimeNet means that most of the hours the accelerometer and the gyroscope has low values. So